Hello everyone, and thank you for coming to our presentation. We are Clean and Green Solar Fuels, and today we're going to walk you through our Capstone project, Solar Fuels Production Unit. Today we'll be covering the project introduction, the problem statement, our goals and requirements, our system design, and finally, our conclusion.
Global warming is a hot topic, and it's not just because temperatures here on Earth are increasing. Finding a way to curb CO2 and its effects on global warming has become one of the grand challenges of humanity is facing today. Many people have been working on this problem, but serious insufficiencies still exist in many of the proposed solutions. Green renewable energy sources solve the CO2 problem, but result in a new problem due to their availability. On top of these two issues, we also have to consider the massive amount of existing technology that still operates on traditional fuels that are not carbon neutral. CO2 levels in the atmosphere are rising, and as global productivity increases, so do our energy needs. We need to address our reliance on fossil fuels if we are going to be able to reduce our CO2 emissions to a more reasonable level. Currently, 43 billion tons of CO2 are released each year, and that's resulting in a sea level rising of 3.6 millimeters each year. Sustainable energy is clearly the solution when it comes to CO2 emissions. But the issue with this energy is its availability. We can always produce excess energy and store it to address the intermittence of these renewables, but the storage of these renewables presents a second challenge. Battery technology is progressing, but has yet been able to keep up with global energy demands. And another technology that's in the spotlight for storage is hydrogen. But the problem with hydrogen is there's not really a lot of end uses that use hydrogen directly, and so we must convert it back into the right energy carrier for it to be used. Lastly, we have many existing technologies that are still in service today that rely heavily on carbon-emitting fuels to operate. 90% of vehicle sales in 2019 were internal combustion engine vehicles. The graph on this slide illustrates this effect in Canada. We have been able to reduce carbon emissions on all fronts except transportation. If we are going to make a dent in the global emissions, we need to find a way to integrate this existing technology into the energy landscape of the future. Our solution must be a renewable energy source. The resulting energy carrier must be easily stored and ready to be used on demand. Lastly, our solution must integrate existing technologies into the sustainable energy landscape of the future. Our solution is to create carbon-neutral solar gasoline that will convert existing vehicles into carbon-neutral ones. Specifically, we're focused on the residential scale.
1,780 liters of gasoline per year is needed, which is the amount of fuel needed to power an average car for a year's worth of driving. This will be created using air, water, and solar energy.
With the simulation system, our requirements have been set to the following. Our system must produce 1,780 liters of gasoline a year. Our panels must remain below 1,700 square foot surface area. Our system must also include displays and scopes for monitoring, and our system must be done by April 2021.
Our system is made of 5 components: photovoltaic power system, direct air capture system, the CO2 electrolyzer, and the H2O electrolyzer takes water from a rain barrel in order to convert that into hydrogen gas. Using that, we create synthesis gas, which goes into the syngas to gasoline plus in order to create gasoline.
Here's a quick overview of our whole system design and how we built it in Simulink.
Here's a quick simulation of what our system would look like in real life. We have the photovoltaic panels on the roof, which should output around 46,000 watts, and we'll also have a rainwater collection system that inputs filtered water into our H2O electrolyzer. Here's a direct air capture system which inputs carbon dioxide in the CO2 electrolyzer, and the produced hydrogen gas and CO gas will both be used in the next process, which is the methanol synthesis. Then the second process is the dimethyl ether production, then our gasoline synthesis, and lastly our gasoline treatment. Our system should output around 1,780 liters of gasoline a year, and this will allow the consumer to fill gas in his car at the comfort of his own home.
Our photovoltaic power system had 3 main requirements. It had to supply sufficient power to a 10.5 kilowatt system, store energy for use when the sun isn't shining, and not exceed 1,700 square feet. quick overview of our photovoltaic power system. On the left side, we have our maximum power point tracker, or MPPT algorithm. We have our photovoltaic array. We have a boost converter designed to output the right voltage for our system. In the middle, we have our load, and on the right, we have our battery and charge controller. And below the model, that is all charge controller logic. Based on a requirement for our system at 10.5 kilowatts, we know that we need 252 kilowatt hours per day. This means for our system, which is receiving 5.5 hours at 780 watts per meter squared, we need to actually output 45,000 watts at minimum. To design a system for this, we needed to have 135 strings in parallel with 2 series modules connected. This had the right output voltage as well as the right, with the MPPT tracking algorithm, the right power output required for our system. For the battery and charge controller, we needed a battery voltage somewhere between 100 volts but no more than 120 volts. And we also needed our charge controller to begin to discharge once the charging reached 99% and began to charge once the battery fell below 10%. So you can see on this slide here that we have a voltage that falls between that allowed region that we've created for ourselves. As well, we also see that the state of charge on discharging begins at 99% and actually does take off and start charging at 10%.
Our system depends on a steady flow of carbon dioxide. The direct air capture system is our method of isolating carbon dioxide from atmospheric air. From a simplistic high-level analysis, the direct air capture system operates by using a simple contactor fan that sucks in atmospheric air. It allows the air to react with other compounds from which a pure CO2 stream can be extracted. Any waste air is emitted from the direct air capture system. On a basic model diagram of our direct air capture system, we calculated it would require 665 watt of power to run, and it would output 0.4255 tons per hour of CO2, which is precisely the amount that we require. We modeled our system off one that was provided to us by carbonengineering.com. Their direct air capture system works on a dual closed loop environment. It separates the CO2 by mixing the inlet air with potassium hydroxide. This then forms potassium carbonate and water. The potassium carbonate is in turn fed into a closed system pellet reactor from which calcium carbonate can be extracted and fed into a calciner. From the calciner, we derive a steady CO2 gas. This gas is then fed directly into the electrolyzer.
Our system depends on carbon monoxide to eventually create gasoline. In order to take the carbon dioxide from the direct air capture and turn it into carbon monoxide, we use a carbon dioxide electrolyzer. So how does a carbon dioxide electrolyzer actually work? Well, if we take a look at the balanced chemical equation for the reaction, we can see that we have carbon dioxide and electrons on the left-hand side, and carbon monoxide and oxygen on the right-hand side. And this is exactly how the electrolyzer operates. We have an input stream of carbon dioxide in which an electrical current is applied. This splits the carbon dioxide into carbon monoxide and oxygen, which are both outputs of the electrolyzer. In order to ensure model fidelity, we needed to find an existing carbon dioxide electrolyzer to base our design on. From this, we found that the electrolyzer should consume between 6 to 8 kilowatt hours of energy per meter cubed of carbon monoxide produced. Additionally, for our system to produce enough gasoline, we need to create just over 7 kilograms of carbon monoxide per day for our STG process. The electrolyzer simulation is comprised of 4 main parts: the electrical system, the carbon dioxide input, the carbon monoxide output, and the oxygen output. The electrolyzer is connected to the battery and current flows into the electricity input. From the chemical equation, the electron flow rate can be calculated based on the current applied and can then be related to the molar flow rate of carbon dioxide. This is then multiplied by the molar mass of carbon dioxide to give us the mass flow rate of CO2 coming into the electrolyzer. The molar flow rate of CO2 is then used to find the molar flow rate of both carbon monoxide and oxygen, and both are multiplied by their respective molar masses to provide the mass flow rate of oxygen and carbon monoxide out of the electrolyzer.
Now that we've created carbon monoxide from our CO2 electrolyzer, we do need hydrogen to create syngas for the syngas to gasoline process. To do so, we've picked a hydrogen electrolyzer, which uses electricity to separate water into hydrogen and oxygen in a process called electrolysis. This entire process has been simulated in the picture that you see in front of you. The inputs for the hydrogen electrolyzer are water and current, and the outputs are hydrogen gas and oxygen gas. We worked backwards from our requirement to produce 1,780 liters of gasoline and figured out the exact mass flow rate of hydrogen gas that's required for our system. Some important SimScape blocks are the controlled current source, which draws in current from the battery, the gas properties and the isothermal liquid properties sets in the actual properties for the water, and the gases, which is hydrogen and oxygen. The controlled mass flow rate source maintains a specified mass flow rate regardless of the pressure difference, and the flow rate sensor regulates and measures the flow rate of water input.
In order to turn syngas into viable carbon-neutral gasoline, we need a gas-to-liquids process such as syngas to gasoline plus. Syngas to gasoline plus is a series of chemical reactions that turns synthesis gas into methanol, and then that methanol is turned into dimethyl ether. Then the dimethyl ether is turned into gasoline. The three most important processes for the syngas to gasoline plus process are modeled in SimScape. First is the methanol synthesis reaction process, where syngas is input into the system. The physical gas signal is split using a flow rate sensor in order to create the physical signal blocks to model the chemical reaction. That is then input into the dimethyl ether synthesis reaction, where the same occurrence happens using a flow rate sensor in order to split the physical signal from the gas signal in order to model the reaction. That is then input into the gasoline synthesis portion, which undergoes the same chemical reaction splitting using the physical signal blocks and is then output as a thermal liquid.
In the next section, we will discuss the preliminary business case of our system by first identifying the stakeholders and their needs, then performing two types of analysis. The stakeholders in this company are the end users and the company. The need this project fulfills is a carbon-neutral and more eco-friendly fuel source alternative. The first analysis is a cost and benefit analysis. First, we will look at the system cost breakdown. This has the cost of all subsystems, as well as the transportation fee and the construction fee. This totals to around $120,000. For the benefits, we looked at the money saved on traveling for gas, the gas price saved, and any additional funding or selling possibilities the system provides. This total came to around $100,000. The next analysis is a strengths, weaknesses, opportunities, and threats analysis. For the strengths of our system, we have our team of engineers and our supervisor, who is skilled in renewable energy and power to X. Other strengths are the system reduces CO2 emissions caused by fossil fuels. It also has expansion ability. It also elongates the life cycles of the input materials. And lastly, the system increases customer comfort as they will be able to tank up their cars at home. For the weaknesses, the system size is large, where people in large land and house can install a system currently, which creates a limit for suburban use. Other weaknesses are the system cost, the efficiencies of subcomponents, which in return produce a low profit margin. The last weakness is in the skill of team members, as we are all from the same discipline. The opportunities of the system is the market for subcomponents that are expanded every year with higher efficiency systems. There is the consumer market, which wants more eco-friendly systems and opportunities. There's also the funding that can be received from the government if we create a system that reduces CO2. The last one, as mentioned earlier, is the opportunity for the system to expand. For the threats of the system, we have the weather, as our system depends on it. There's also a major threat that there is not much research on the topic, which opens up the idea to many other companies, which can cause a large competitor base that could potentially cause negatives to the system we produced. Overall, the system seems to be successful, and it also has a payback period of a year, which is good for a new startup.
To conclude, we've met most of our requirements except for the square footage allowance that had to be exceeded to get the power that our system required. For that reason, we proposed our system on a larger scale, such as commercial, agriculture, rail, and even existing refineries.
Thank you so much for watching our Capstone video. We look forward to hearing any questions from you come Capstone Day. Thanks again.